So today's topic is some simple inequalities. Okay, simple. I will be starting with numerical. Okay, simple numerical inequalities. Okay, so numerical, you will see how what it means and how it's different from the algebraic inequalities which you may have heard, AMGM and so on. I don't know if you have done that, but you may have heard, may have done. So let us just start with a problem in this. Okay. So how can I start? Okay. Let me ask you for two-digit numbers. So Unab, can you tell me two-digit numbers? Any two-digit? Okay, 13 and 39. Okay, I'm just asking because so that these are completely random. Okay, and Pragya, can you tell me, and Ishana, one each, one more, two-digit numbers? 32. Yes, Ishana. 54. Okay, so we have these four two-digit numbers. Now I'll just cook up a question from here. Is okay, just I'll ask like this: is 13 to the power 54 here, and here let me take 42 to the power 39. Okay, which one is bigger? So four random numbers, and which one is bigger? So maybe you guys have thought about this earlier, I don't know. Ever? Is there a good way to decide? Okay, so you are saying it is like this. Okay, why do you think so? Thirteen raised to 3 times 18. Yeah, so it won't be 3 raised to 18, it will be 3 times 18. Right. Okay. 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 So let's give ourselves some time and think about this. It's like an MCQ type question. So any ideas? Obviously, we don't want to calculate the numbers. needless to say. But obviously, we will need to do some calculations in the end, maybe, or at some point.
It's like third, 42 raised to the power 39 is definitely bigger than 13 raised to the power 39. So if there is a difference between the two, and now is this difference bigger or smaller than 13 raised to the power 15?
15. So, okay. No, but that will also not be enough, right? Because you understand, right? I mean, this plus this is not bigger than 13 raised to the power, right? So if you're saying that this difference is, like, even if this is true, then you get, oh, you only get this. So that is not very similar to 13 raised to the power 54, right? Yeah. So it's not about the difference effect, it's about the ratio, right? It's about the ratio of, so you can ask, what is the ratio? So that's, so you have made a good observation. So you want, what you should ask is, what about the ratio? Is this ratio bigger than 13 to the power 15? Does this sounds correct, right? I mean, this is correct. You can just check, right? 13 raised to the power 39. You are kind of bringing that down here. So why am I writing greater than? I'm saying just question mark.
Yes, sir.
Yeah. But is this an easier question or not? That is, you have to think. But maybe this can be used to finish the problem, I think. So let's think. Just cleaning this. So this is, so this I'm keeping on one side because this is one potential approach. Okay, okay. So if you write this as 3, then what do you have in mind? Okay, this is a much simpler thing to check. So maybe we can believe this. Okay, we can believe this. Oh yes, yeah. So that's a good way to say maybe. 13 into 2. But what does that have to do with? No. That's not a correct explanation. But let's assume this. That we can reason out with other ways. This is much smaller. Okay. So then this solution is done, because so we should not use the word. I mean, you should use approximation to get your answer, but you cannot use that while writing the proof. Means it's wrong, because you what you need is 3 being less than 42 by 13. Right, which is true, but you need to use this. Okay, that 3 is less than this, and so now you can understand. It works. Okay. So anybody has any questions here? Okay, right. So in some sense, it was good that so let me write it in words. Okay, we wanted to show that 13 to the power 54, or we wanted to, let's say for a moment that we wanted to show that 13 to the power 54 15, because we divided, is less than 42 to the power by 13 to the power 39. Okay, but it is enough to show that 13 to the power 15 is less than 3 to the power 39, because 3 is less than 42 by 13. Okay. Because we're discussing these inequalities for the first time, it's important to understand what you've actually done. Okay, why I'm writing here, it is enough to show. It means that, look, yeah, if you show that 13 to the power 15 is less than 3 to the power 39, which we have kind of shown, then it's enough, because 3 is less than 42 by 13. Okay, but it might have happened that this was not true. Okay, so what I'm saying is that it might happen, might have happened. I mean, you understand, might happen that 3 to the power 13 is bigger than 39, but 3 to the power 13 is less than this. Okay, it's in between. This might have happened, right? On the number line, to the power 39, and it might have happened that 3 to the 13 to the power 15 is kind of in between. We were lucky that it is not, and so it was, our proof worked. And usually this method works, this kind of thing, approximation works. If this would have happened, though it does not happen, then our method would have not worked. Okay, so my point is that if, so let me write it here in general, and this is learned as you do more questions. You'll see that if we want to show, it's just a logical question, we want to show A is less than C. Okay, if we know that B is less than C, okay, then enough to show A less than B. But this may not be true. Okay, if A less than B turns out to be true, then you are lucky, you are done. But if it is not true, then you should not think the problem is wrong, or you understand, right? It's not necessary. Okay, but it might happen that A is kind of in between. This might happen. This is a possibility, obviously. Okay, so you're approximating C with B kind of, but you have to be careful. If it doesn't work, then you have to look for something else. Okay, so this is just the general thing that we're learning through this. But yeah, this is a good solution. So the point is that it is kind of problems. You have to just do these ad hoc things. I mean, there are some patterns. Okay, but in general, if you don't see any pattern, then you have to follow some ad hoc method like this if it's an easy question. Otherwise, obviously there is no fixed method. Okay, yeah. So this was a good thing, right? We basically worked on the power. Okay.
When she said that like 27 is almost twice 13, so you said that that is not a good explanation.
Okay, so why should that be a good explanation?
Sorry, 13 to the power 15 2 to the power 13.
Okay, 2 to the power 13 into okay. Why? Because why?
Can cancel and then 13 square is less than 2 to the power 13.
Oh no, sorry, sir. You are no. So can you say that again? Which part? What came?
So it's correct. What you wrote.
Okay, but why is this true? Okay. Yeah, but then you get to this, but this is not correct. Oh yeah. Sorry. This is true. Yes. Okay, right. Okay. Okay, so you're basically using the fact the rest of the thing is double. Okay. But you see, again, this is because this is equal to 26 to the power 13. Okay, but that is, yeah. So as it works. Right. So in that sense, okay. So I didn't mean it's a bad explanation. But I did say that, right? Okay, I didn't actually understand why it was a good explanation then. It works. That's correct. Right. Okay. So you see, the key was that we kind of reduced the question to this. Right? But here you see, if you notice one thing in this problem, that we kind of use the fact that 54 and 39 not so far, right? But otherwise, this may have not worked so well. Okay, a slightly alternate way is by, I just say alternate way, I'll not say a better way, just an alternate way actually, is to do this. And you can appreciate this. This might be better and suited in other kinds of question. It depends. Another way is to see, we do this, right? We take a number A and we do powers, right? Powering. Yeah. So see, powering is like an operation, right? Suppose you fix a B and then you take every number and you power it. You go to bigger number, A to the power B, bigger in this case. But you can also come reverse, right? You can come reverse by taking the B at square root or something like that, right? So I'll kind of use that idea. Let's see if that is useful here. So I'll say that the comparison between these two, comparing these two is the same as comparing. I mean, I'm not writing comparing, maybe I can just say this question mark, whether this is less than this or not, is the same as if we take square roots, fourth roots, things like that, but I'll be taking 39th root. Does everybody agree with this? That why these two questions are the same? Like if the first is true, then the second is true. Maybe I'll write like this for a minute. Right, then you can get the first one right. Right. And if you do both sides to the power 39, then this less than will not suddenly become greater than, right? This will remain as it is. Okay, so what we are using, again, this is something that all of us know, is that if A is less than B, then A to the power C is less than B to the power C. Okay, is this always true? Right? This is always true for any positive number, right? If they are positive. So they don't even have to be bigger than 1, right? Or do they have to be? No, right? Is there any condition on C? Right, can it be negative? No, C has to be positive, right? C has to be positive.
If it is negative, then
It will be the reverse. It will become reverse. Yes, that's absolutely correct. Yeah, if it's negative, it will actually reverse. Right. So, but we are in that safe situation, so we can do this. But does it simplify the question? Let's see. So the idea is that usually this will, is more tractable. Okay. So this is what? This is, I mean, here we can divide, but this is like 1 point, is it more than 1.3? That we can roughly estimate, right? You can just take the, yeah, it's like 1.4. Okay. So it is more than 1.4. Right. So if even if but it's less than 1.5. Okay, it's less than 1.5, right? So even this, yeah, I mean it is certainly less than 1.5. Yeah, even this is this true? Is this true? Now that's not hard to check, right? Because you can take square root of 13. Wait, but that's not true. Hold on. Oh yeah, it is true, obviously. Yeah, this is true, right? Because you understand this is 13 times what? This is okay, what is this? I don't those things you can check, right? You can finish it. Dot dot dot.
it will be less, something less than 2.
Yeah, but that is not enough, right? We have to be a little more precise. Yeah, maybe you can say 3.5 or something. I don't know. You can do it. Yeah. Or then you have to use a better approximation here. You see, but this also is a way. That's all I need to tell you guys. Like you can do the calculations. Okay. These are these are the ad hoc ways. Okay. Now, if you are provided with a log table, then you can take logs if you know what. Obviously, maybe you know, but these are the various ways. Okay. Yeah. So basically, I didn't do anything. This is a variation which, yeah, can come up. So you see, very simple. Okay. But this, you see, this raises a fundamental question. Okay. So, okay, let me first tell the theme. So we want to go from numerical inequalities. So what we are proving right now is not so mathematical. It's more like computational. What we are doing right now, it's not mathematical, it is computational, mostly, like purely computational, in the sense that our truths that we are establishing are not so general. This is not a very general truth. It is just the truth about some 4 numbers, right? Some a fixed 4 numbers, in fact, right? If you change the numbers, then maybe you have to do something else. But we want to say some general truths, right? A, B, C, D, then if if a is bigger than b and something, then this a to the power b will be bigger than c to the power d. Something like that you want to be able to say, if it's at all possible in some cases. Okay, so the point is that we want to go from these numerical inequalities to what I will call algebraic inequalities. Okay, it basically means more general truths. Yeah, saying it in general about some variables, maybe with some conditions. Okay, algebraic inequality. Like, I'll just give you an absolutely trivial example, right? So we know that 2 square is bigger than 0. We know that minus 2 square is bigger than 0. We know that minus 4 square is all this, right? What's the general truth behind these numbers, behind these things? That a square is bigger than 0 when a is real. Yeah. So we want to see if we can say a general truth, more general, something that applies more generally. So yeah. So we want to go from here to some algebraic inequalities. Okay. So what is a natural, or what's the first, or rather, if we just translate this question to algebra, an algebraic generalization, then what would the question become? Okay, given A, B, C, D, okay, which one? So we're just doing a first step translation. Okay, this is the way we do things, right? We prove something for some numbers or some terms, and we try to generalize it. Okay? This is like that. Given A, B, C, D, which one of a to the power b, c to the power d? Now you see, it doesn't matter. If I would write a to the power c, b to the power d, question will not change, right? Because a, b, c, d don't have any relation till now. Which one of this is bigger? Now, obviously, this question doesn't make much sense, right? Does it? Yeah, nothing is given, right? So now I want you guys to give some conditions. Okay, so do your try to bring your own conditions. Okay, so come up with conditions, and this is an interesting question because you can come up with conditions, you can try to write it, and so on. So come up with conditions on A, B, C, and D, some relation or some A plus B equal to C plus D, something like that. I don't know. That is completely open. You can come up with 100 different conditions. For three of you can come up with 3 different conditions. Okay, and that's an interesting thing, because you come up with conditions on this such that question is not complete, such that A to the power B is bigger. Let's keep this. There's no problem in this, right? I mean, the other way, you can just take the opposite condition, right? So come up with conditions A, B, C, and D such that this happens. Maybe you can put equal to. Now, obviously, there are some very trivial conditions. Okay, I'll do the trivial work. Okay, example, if A is bigger than C and B is bigger than D. Okay, bigger than equal to also works. Then I'm just writing it. Okay? Then, but can we say anything more interesting? That is, and there are many interesting things that you can say, numerous things that you can say, unending number of things maybe. But some simple things that you can do at your level, at our level, that we can understand, try to come up with. But I will do in the class one condition today. It will be simple enough, so don't worry. Really very simple again. But this, take it as a good opportunity to actually do your own, come up with own things. Very interesting, because it will be easy. You can just take some tests, some numbers, and you can try to do. But let me do one of them now. So yeah, the way I write things is a little not so well arranged. Okay. So here the question is, any other interesting condition? So this is certainly one trivial condition. One trivial case in which this holds. the question is any other interesting condition? Because then you'll be establishing general truth, right? If you just put some other condition, quick condition, and you are able to say, then it means that you'll be proving it for so many numbers. Obviously, you should not say that A is equal to, you can't say another condition is A equal to 13, B equal to whatever we just did. Because that's not really a condition. That's just a case maybe. It's a condition logically, but it's just a case in meaning, right? Oh, okay. Yeah, but that's not a very good condition, right? That's again a very simple condition. Yeah, that's even, I'll say it's even worse than this condition. This is simple. Yeah. Yeah. I mean, it is in fact contained in this condition. And so, yeah. So any other interesting conditions? Yeah. So let me ask this. Okay. If C is equal to B, because this is actually a very fundamental thing later on, you'll see it's connected with E and pi. Okay, later on in the theory of calculus, and it's actually a pretty interesting thing. But for now, we'll just try to do, let's see, if C is equal to B and D is equal to A, then what can we say? Think about this. We'll do this now. I mean, you can just take some examples and also at least make a guess first. So then the question just reduces to, I just I'm just writing it, nothing new. Question is then,
We can say this will be
okay, why? 2 to the power 18 in the power 2. Okay. Um, okay, so let's write that also. 19 to the power 18. Oh yeah, that I agree with you. That makes sense. Yeah, as the difference becomes bigger, it becomes easier. Right. Um, right. And so these two are obviously true. You can check. I mean, this one is obviously true. This one is not so obvious maybe, but you can check that it is true. 1 minute. Wait, what is happening? No. I don't know about this actually. Is this true? You guys can quickly tell me by the methods that we just did. Or you can. I don't know if this is true. Okay, maybe it is not true. I should. Okay. Yeah. Right. I also think that. So how can we check? We can just do something similar that we just did. To the power 18, and this is bigger than. Is this bigger than 18? That's the question. Hard to know, right? It's hard to know. Yeah. I mean, a lot of things are done by binomial theorem very well. I know. I mean, I know the answer by some theorem that I think this is not true. But yes, yeah, that's the next thing. Yeah. So you see, in this case, this is a little tricky to understand if this is true or not. But yeah, we can do 18th root. That is good, maybe, right? So if we do 18th root, then we get 19 by 18. But it comes down to the same kind of thing, 1 plus 1 by 18. So maybe that method will also work, but right. So then what can we say? What can we say? It's tough to say anything. So 1 by 18, can you approximate? No. Is it 1.5? Sorry. No. Why will it be root 18? It's yeah, 18th root. So yeah, so I don't think then my technique maybe is not so good here. It doesn't even work here. Well, let's think. Right, 1.05, and then you have 18 to the power 1 by 18. So then from here, a little bit of binomial theorem, if you have done, then it can be done very easily. But otherwise, this is how to do. We can approximate it with 1 by so if I write here 1 by 20, 1 by 20, 0.05. Yeah, so then it is not so difficult, maybe, right? You can no, so it is bigger than 2. Yeah, so it seems like this is bigger, right? 0.0, no, so 1 by 20, that's 0.05. Yeah, it seems like this is actually bigger. But how to show quickly without any theorems? So this actually tells us that we are lacking in a lot of theorems, right? We need to know more theorems, and we need to try to prove more general truths. But this is let's see if we can do this thing. Let's see. Yeah, that might be. Well, let's see. So if I'm doing here on the top, okay, so let's do 19th root. That is 90 by 19. And we are trying to say this is bigger than 18. And this is a question mark. Yeah. Okay, why? Yeah, that's right. But yeah, As it's not such a, we are not really, our method is not so good. So 18 by 19 is, 18 by 19 is bigger than 19 by 20. And this is bigger than 0.95. But again, it's hard to say anything. No, this is, I mean, again, with some calculations, maybe you can take the 20 that side, and then you can come. Yeah. That's the real thing. Yeah. Like maybe you can then reduce it to this if you power, and then again you can do something maybe, right? I don't know. Yeah. You can maybe do again something. So it's just you have to try some different things. Yeah, maybe 19 by 18. You can, so you can do like this and get this, but then it's down to the same thing. Okay, we're really stumped in this. So that's not a problem, right? The point is that that's why this is a non-trivial question. And so to answer this, maybe you can take some other examples. You can take some other examples and see. So take some other, this example is not so good, no problem. Take some other examples, right? So in this case, this is true. Try some other examples and see what's happening. It's not such a good example numerically. So yeah, that's why the numerical inequalities, it really depends on what numbers is chosen. So usually they'll not choose a bad number, so that works out. So actually the point is that proving this you will see is eventually easier than actually proving the specific cases. Okay, because of proving this, we will be having a better view of some things. Then we can prove it, but we'll see that later. First, there is at least know what is truth, which side is true, bigger or not. So try some other examples. Maybe you can take 3 and 5, a equal to 3 and b equal to 5. Right? 3 to the power 5, 5 to the power 3. Which one is bigger? 3 to the power 5. Right? So you see, whenever, so it's, now this is very clear that whenever a is less than b, it seems to hold. Right? So I'm just removing the examples. You can, okay, I'm keeping examples here. So what I'm trying to say is this is true whenever a is less than equal to b. It seems like. Right, yes. I mean, at least for after 2 and so on. 2 and 3 you can check. It's probably not true in one of the things. Yeah. But beyond a certain point, it is true. Okay. Obviously, you will need a less than b, because if you reverse it, then it will not be true, right? Because then it becomes b less than a, right? So it's the opposite thing. So this is the conjecture. Okay. Try to prove. Try this for homework. This may not be, I don't know if this is easy or not. I know a method, but let's see if there are other ways. Okay, so please note this down and try it. Maybe you can even assume that a and b are natural numbers and so on. That doesn't really matter. But let's see if you can do a proof. Okay. So think about this. This is a very interesting, it's a very fundamental question, important question. Yeah, so this was one of the conditions. Okay, now come up with some other conditions. Come up with some other conditions. So you can also use the intuition that powering is creates more impact than, changing B will create more impact than changing A by the same amount, right? If you change B by 1 or 2, that will create more impact than changing A by 1 or 2, right? You can kind of feel these things are correct, right? So maybe try to, see some example, do some examples and try to put some conditions. Okay. So yeah, this is an open-ended question. Please at least come up with some condition. You will be able to. It may be very simple condition, not so, useful, but come up with something. That's very important. Okay. So this is the thing. Now let us move forward. So yeah. So what should be the next thing be? Right. So let us now change a little bit, okay, and let us look at factorials, okay, because factorials are also kind of interesting, important and interesting numbers. So we'll try to compare factorials, compare factorials, compare. So again, we'll keep it simple to begin with, and we'll ask some very simple questions. Compare n factorial and n to the power n. Which one is bigger? Right. So this is very simple. Now let us compare. Is this okay with everyone? Okay, so this is absolutely simple. Now let us think about this. If you take not n but n by 2 and multiply it n times, then which one is bigger? Now I may have done this with some of you earlier. Okay, I don't know. I think we did it to some extent in compare. I mean, see infinite series you were doing. Some people were there. Yeah, but yeah, let's see if we have done the specific one or not. Maybe we have not done this specific one. I think. Okay, well, if you can take some examples, 4 by 2, maybe this is very less small example, but right. So it holds. It holds in this case. If you take n equal to 5, okay, I won't take 5. Again, we'll get some decimals. Take n equal to 6. Then we get 3 to the power 6. But now it is not true. No, is it true? What is 3 to the power 6? 729, right? Yeah, it is true. It is still true. Okay. So let's think. No, no, sorry. It's no. It's the other way now. Yeah. So it's okay. So then it seems, yeah. So you have to now think. Take some more numbers and try, and then see. Then make a guess or some other way. these inequalities are used time and again in because factorial is not such a good function, right? As a function, it's not such, doesn't have such a implicit definition, right? The definition is kind of multiplying the previous and previous. But n by 2 is just a power, n by 2 to the power n. So these inequalities will be later used in comparison while doing limits, and if you want to approximate an answer or show that some counting problem's answer is some bigger than something or lesser than something, these kind of things can be used. If you take some more examples, you should be clear that where it is going. I think it is okay. It's n factorial. That's right. Yeah, but after that, the story it reverses, right? Yeah. So yeah, basically we want to understand what happens when n is big, right? So yeah, so it is now a very clear conjecture, very clear proposition to make, though maybe not trivial to prove, is that this should be true. Let us contemplate how we can prove this now. By 2 raised to n. Yes, obviously, yeah, we can, because again, the truth will not change, right? So you can say this is true if and only if, yeah. Or you can also first do the proof and write it backwards, anything. Okay. Yeah, I was just thinking of a combinatorial proof, and this I brought in 2 to the power n also in my mind for that. Anyway, let's see where this is going. What this. So this is n to the power n. Yeah. Yeah, but when you multiply by 2 to the power n, then it can change or it will not change. Not difference. No, again, it's not about difference, it's about ratio, right? About ratio. Think this is a new thing, maybe. But it is not very new. For example, you can think about this. This is very simple. Uh, and similar kind of argument is used. But okay, not similar actually, sorry. A little different maybe. Okay, like what number you have taken? No, but this was not true. This is true for n bigger than 5 or n bigger than equal to 6 maybe. Right. We already said and we already know, right? It's not true for 4 and so on, right? It's true after a certain point, like after 6, like from 6 onwards, definitely. Okay. Yeah. So maybe this one is then slightly new for us, right? Try to try to do like this maybe. So one way is induction. Okay. If you know induction, then you can kind of say, let's assume this is true and I'll prove for the next n plus 1 case and so on. But I'm not going to do like that. That is, you want to see it in a different way. So you can try to write this as 1, and it's a very general method, sort of like a balancing technique. And then you have n by 2 and you have n of them. So we're writing their actual meaning. N by 2, n by 2. 1 minute, let me not write it here. Let me write it here in big, because It's n by 2 to the power n, then it is n by 2, n by 2, and so on. This n times. And then if it is n factorial, then it is, so I'm doing it in this version. You can, it will be same, but let me do it like this because it actually says something, something more maybe we can learn from here. That this we do till n by 2, assuming n is even, doesn't matter. And then from here again till n, right? Now you see, till this point, n by 2 to the power n is winning, right? Every time it's bigger numbers, right? N by 2 is bigger than 1, n by 2 is bigger than 2, n by 2 is bigger than, okay, till before n by 2, right? After that, n factorial is winning, okay, because you get n by 2 plus 1, and so on. So, you know, it's, yeah, so it's not straightforward. Yeah. So how can we still compare these two things? So you kind of balance it. How you balance it is, you take 2 of n by 2, and then you ask the question, is this bigger than 1 times n? And then you take this and this. So I could say you take this, and you see, you multiply and see, right? So this is making n by 2 to the power n win, and this is making it lose. So then you take the net effect, kind of, right? Taking the product, which one is doing it more eventually. So you look at this, and then you can similarly keep doing this, right? You can take n by 2 times n by 2 and compare it with 2 times n minus 1. And in this way, you can continue and ask these questions. Okay, so do you guys see what I'm doing? Yeah. Yeah. Comparing. Yeah. But we are kind of crossing and comparing, right? That's very natural, right? Because half the time this is winning, half the time that is winning. And so you kind of cross and compare so that you can see the effect. Okay. So that's why we are doing 1 times n, 2 times n minus 1, and so on. So now think about this. Try to complete it from here. Okay. Dot, dot, dot. Means we will discuss this further with more, some more things, and we will, from here, we will move into sums and products, comparing basically AMGM and so on. Okay. But please try to finish this. This is a good exercise. Like you can see this is bigger, then you can maybe show this is also bigger, and so on. See how you will reason out. Yeah, so that's it for now, I think. Yeah, I do have a few more things to say, but maybe we can say it next time. But let me ask one more, let me not ask, but just give one more question for you guys to think. So this is definitely there, you should do it. And there is one more question which is rather interesting. So we know that n factorial and n and so on we compared, right? But what if, like, this was very simple? This is very simple. But what if I divided by 2 and I asked, and it is still true? But can you compare this? It's a question mark. I'm just asking you to compare. I don't know. It's a natural extension, right? And by 3, I will try to compare. Okay. Think about this. Yeah, just think about it. And the next question also I can ask is, okay, what if I put another factorial? Then who is winning? Okay. And maybe you can also ask, what if I put another factorial and I say, okay, I'll raise this like this. And this means you first evaluate this and then you evaluate this, and that matters. and you can ask this. And similarly, you can put 3 factorials and ask. So try these questions. Okay, try all these variations. All these questions have, I think they have good answers. Can they lead to different kinds of theories? Okay, this will you'll see. Yeah, so try this. Okay, you have a lot of things to try. Earlier also we said earlier problems and this also. Okay, try this. So basically, we're starting with these numerical questions and then we're trying to generalize. Okay. Yeah, so you have enough work now, your hands, to try these things. Yes. Okay, then. I think that's it for today. Yeah. Any questions? Anyone has questions? Okay, everybody understood. Okay. Okay, then. That's it. Thank you. Bye.